Okay, so we're going to pick it up where we left off with our discussion about integrating with partial fractions. And we've already done several examples. In fact, I want to start again with this last example that we were working on. And so that would be this one. Okay, yes. So now if you recall, the way this works, what we're looking at here are rational functions. We have a function in the numerator, a function in the denominator. The technique that we're using here requires us to have a smaller degree in the numerator than in the denominator. Okay, they can't be equal. It can't be the case that the degree of the numerator is larger. If that happens, what we need to do is reduce the problem with division. And we've already done an example like that. But here you can see that the degree of the numerator is 1 because x has an exponent of 1 here. That's the highest exponent of x in the numerator. And down here, the degree is 3 because the highest power of x is 3 in the denominator. So for this, we're all set. We can go ahead and use the method of partial fractions directly. And so what we do want to do first, though, is look at this denominator and see if there's some way we can simplify it. So let's just take a look at it. So what do we have here? X cubed minus x squared minus 2x. Now, obviously, we can factor out an x, and that helps a lot, because now we can just factor this quadratic expression into x plus 1 and x minus 2. Now, by the way, how do we know that this is right? Well, we can double check this with FOIL. This would be F O I and then finally last. Okay, so that means that this expression can be rewritten as x plus 1, and x minus 2. That's what we need to do the method of partial fractions, because we're going to create 3 fractions with these terms. Okay, so you can see we did this in the next slide. And so the original expression on the left can be rewritten as a over x. Okay. This is one of the 3 factors of the denominator, plus b over x minus 2, plus c over x plus 1. Now, the denominators on the left and the right are equal to each other. So, or they will be, sorry, they will be as soon as we do the following. What we want to do is create a common denominator. Okay, and how do we do that? Well, the common denominator, typically the easiest thing to do is let this be our common denominator. So we can easily create one for all of these terms. So here's what we're going to do. For a, we'll multiply it by these 2 factors over themselves. In other words, we only have an x here. In order to create a common denominator, we also need the x minus 2 and the x plus 1. In order to avoid not changing this problem, we need to multiply a over x by a ratio which equals 1, and we're choosing x minus 2 times x plus 1 over itself. For b, the 2 factors that we don't have here are the x and the x plus 1. So that's what we'll multiply this expression by, x plus 1 over itself. The c is just missing the x and the x minus 2. So by what we've done here is we actually multiplied each of these terms by 1, which we're certainly allowed to do, but we needed to do it in such a way that we end up with a common denominator for all the terms. So what we have here then ultimately is a x minus 2, x plus 1, plus b, x plus 1, plus c, x minus 2. The denominator is the three terms from the original expression. Okay. Now, so let's see, I can sneak this up here. So what this means is that this original expression, oh, I don't think I'm going to have enough room here. Let me try this in the next slide. Hold on 1 second. Yeah, that might be the way to go. So again, we started out with 3x plus 2. Over x minus 2, x plus 1. And we demonstrated that this is the same thing as okay, so we had a times x minus 2, x plus 1, plus b, x plus 1, plus c, x minus 2. The denominator is this expression. Anyway, so because of the way it's written, what this implies is that the two numerators must equal each other. That's the bottom line. And so really what we're trying to do here is gather up all the terms on the right so that we can set them equal to what's happening on the left. So in other words, if I do that here, what I'm going to do is simplify it a little bit. I'll multiply these together using FOIL. X times x plus 1 is x squared plus 1. And here we have x times x minus 2, which gives us x squared minus 2x. So now what I'm going to do is gather up all the terms, all the x squares, into one set of parentheses. All the x's come over here. And then all the constants go here. There's only one left. So what this means then is that now there's no x squares on the left. That implies that a plus b plus c is equal to 0. There's a 3x on the left, which tells me that 3 equals minus a plus b minus 2c, and the constant on the left is 2. And so this is what we're left with. We've got 3 equations and 3 unknowns. So this part can be a little bit challenging. Usually the best bet is to solve for one of these in terms of the others, and then make some substitutions. And, you know, it can take a while sometimes. It depends how messy the results are. But here, it's pretty straightforward because you can see in the bottom that a is -1. So we've already got one of these out of the way. And we can then plug this into the other two. And so what that means is I can now write this as, let's say b equals 1 minus c. And that means now with the second equation, I can make some substitutions. Minus a is just minus 1, plus b, which I'm writing as 1 minus c, minus 2c. So I'll have 3 equals 1 plus 1 minus c minus 2c. So therefore 3 equals 2 minus 3c. 1 equals minus 3c. All right, so we have 2 of them done. And now we have 2 of them. We can put the definition of A, or these constants for A and C, back into, let's say, this one, and solve for B. All right, so 0 equals A plus B plus C. And we just got through showing that A equals -1 and C is -1/3. Okay, so just to recap, A is -1, B is 4/3, C is -1/3. So now what do we do? By the way, there's a lot of different ways you could have gotten to the same point. With the substitution method, there's all kinds of ways you could have gotten to the same point. It's like driving somewhere. There's a lot of different roads that lead to the same location. As long as you got the same 3 constants, you'll be all set. So going back, this one, yes, let's grab this one. Okay, so once again, a quick reminder, A is -1, B is 4/3, and C is -1/3. So what that means is when we integrate the original expression, we're integrating A over X, which is -1 over X, B over X minus 2, which makes it 4/3 over X minus 2, and then C is -1/3. Now we can break these up into the 3 separate integrals. And this is a good idea because each one of these may need a different approach to be solved for. So this way you can treat them all individually. Like here, the first one is already, we know this is the natural log, okay? But the other 2 will certainly want to use U substitution for them. Okay, so this one will just end up being but these next 2 here, you could try, for example, U equals X minus 2. And you've already got that, you're all set. And this one, you just simply let X equal U equals X plus 1, so that du is dx. And you have that here too. So you're all set. So here's what you end up with. This one became 4/3 U du. And then this one one-third ln u, one-third ln x plus 1. So combining all 3 of these, and this one, of course, we've already seen, is the negative log of x, absolute x, that is, plus 4/3 log x minus 2 in absolute value terms, minus 1/3 log absolute x plus 1 plus c. And that's it. You're done. By the way, I've noticed from trying, this can be rearranged in quite a few different ways. If you pop this into Symbolab, it may give you a different looking answer, but it'll ultimately be the same thing algebraically, because I don't know if you can specifically tell Symbolab what technique to use to integrate. I tried it before, I just popped it in, and it did a completely different technique. And it came up with an answer that on first glance looked wrong. But then after doing a lot of algebra, I was able to prove that Symbolab had done it correctly. But because they used a different approach, it appeared to be different. And that turned out not to be the case. So that's good to know that even if they use a different technique, you'll still get maybe a different looking answer, which actually has the same value. And of course, if you want to, you can prove that this is correct by taking the derivative of this expression, just to make sure, if you're not positive that you did it correctly. There's nothing to stop you from double checking it. So here, how would that work? If you take the derivative of this expression, we don't have to worry about the c because we know that that'll just be 0. So we'll have now here you would have to combine these. Ooh, I'm running out of room, I can tell. All right, let me just move on to the next slide. It's sometimes it works and sometimes it doesn't. So let's see what that turns out to be. And we're hoping that it's the same as what we started out with. So this will be the numerator of our expression. Now, all of that will be divided by x minus 2, x plus 1, which was the original equation. Now, remember, in the original problem, what we had was way back here. Yeah, so in other words, 3x plus 2 is in the numerator. The denominator is x cubed minus x squared minus 2x. So what that means here is that what we really need to do to make sure this works correctly is prove that the numerator is equal to 3x plus 2. You can see that the denominator is correct. So in order to prove that we did not make any mistakes, what we need to do is show that 3x plus 2 is negative x minus 2x plus 1 plus 4/3 xx plus 1, and then finally minus a third xx minus 2. All right, so the right hand side equals, now when you multiply these two terms together, x minus 2 solve this with FOIL. But don't forget about the negative. Okay. O is x. I is negative 2x. And then last would be these two minus 2. So without the negative sign, it's x squared minus x minus 2. With the negative sign, this becomes negative x squared plus x plus 2. All right, so recapping this, we have 3x plus 2 equals, again, negative x squared plus x plus 2. And then what came next was this part. Now this is equal to this. Okay, so let's write that in. 4/3 x squared plus x. And then the last term would have been okay, so this is going to be minus a third x squared minus 2x. Okay, x squared minus 2. All right, so now we can start doing some consolidation. All right, so let's gather up all the terms with the x squares. Then we have the x's. And then we have the constants, 2, and that's it. All right, so we're so close. Now, these, negative x squared plus 4/3 minus a third, all of this is 0. Because you've got minus x plus 4/3 minus the third, that adds up to 0. And then down here, if you add these up, you've got 3x. So you do ultimately end up with 3x plus 2 equals 3x plus 2. And that means we did it. So yes, it was a bit of a headache, but we had the satisfaction of knowing that this is the correct answer. okay? And again, even if you throw this into Symbolab and it looks different, you could prove that it is the same thing. They did not, when I used it, they did not choose to use partial fractions. I don't know if Symbolab, I'm going to see what I can do about this. Hold on a second. Can I specify a method for integration? Oh, maybe they can. I'll be damned. I had no idea. All right, let's try this. Sometimes I'm so frustrated with this thing, and sometimes I'm very impressed with it. So we have the original expression was 3x plus 2 and in the denominator we had x cubed minus x squared minus 2x. Now, by the way, I am subscribing to the full version of this thing, so it's possible that you won't be able to do this. I don't know. I'm not sure how to tell. I decided to bite the bullet and pay for the full version of this thing. And so I'm not positive that you also have access to this. So you can check it out for yourselves. Oh, it wasn't expensive at all. It's like a few dollars a month. All right. Negative a third. Log x plus 1 in absolute terms, 4/3 x minus 2, negative log x. There you go. And then not only that, but they're offering to show the steps. Now, again, they may do it slightly differently, but you'll ultimately get to the same place. Yeah, well, their explanation is a little strange, but there it is. Okay. Now, in the next section, what we're going to do is something interesting. We're going to actually combine two different techniques to get our desired integral. So what we're going to do is use U substitution before we apply partial fractions. There's nothing to stop us from doing this. We can apply as many techniques as we want, as long as it works. So here's a good example of this. All right, so we have cosine x over sine squared x minus sine x. Let's try u equals sine x, which means that du is cosine x dx. And so that means that we could rewrite this as, again, u was chosen to be sine x, du is cosine x dx. So all of this is du, and that leaves us with u squared minus u, or, aha, now you can see, now it should be clear why we can use partial fractions because of the way it's written. So here's what we're going to do. And take it from there. Now, if we tried to do the partial fractions directly on the trig functions, we would have gotten nowhere with it. This technique is based on the assumption that we have either linear or possibly quadratic factors. That would not have happened if we had trig functions. So then, of course, we'll cross multiply. A will need to be multiplied by u minus 1 over u minus 1. B will need to be multiplied by u over u in order to have a common denominator. Okay, and since this is what we started with, we'll set the two sides equal to each other, the numerators must be equal. And so, because there's only a constant here, actually, this should probably be rewritten as 1 over u minus 1 is a plus bu minus a. And you can see, because on the left-hand side there's no u, that implies that a plus b is 0, and then 1 is negative a, or of course that means that a is negative 1. So if a is negative 1, b is 1. All right. So that means this expression can be rewritten in the following way. And now we can integrate both sides with respect to u. And when we're done, we'll, of course, substitute the value of u. Remember, u equals cosine x. Okay. So I broke it up into 2 pieces, which is usually the easiest way to go. And then we have negative log u, or absolute u, plus absolute log of absolute u plus 1. And of course, don't forget that u is the sine of x. Therefore, we have negative log sine x plus log sine x plus 1 plus c. And now we know that we can tell Symbolab, actually, this is a combination of 2 factors. Or 2 techniques. I'm guessing that it could handle this. I'm not sure if we can specifically ask it to use both method of substitution and partial fractions. It looked like there was a list there, but just one at a time. Anyway, now here's what we're going to look at. This is the end of the chapter, by the way. We're going to consider a case where the factors are a little bit more complicated. Taking the form ax plus b to the n power, we're going to call those repeated linear factors. So you could, now let's say it's something like this. Well, it turns out that because this factor, 2x minus 1 is squared, that introduces a wrinkle into our calculations. In other words, we're not going to end up with a over 2x minus 1 squared and b over x minus 1. We have to take into account the fact that one of these terms is squared. And so here's how we allow for this. In other words, here's the technique that we'll use. Now, here's what we had to do. We've got a over 2x minus 1, and then b is over 2x minus 1 squared. And then c is x minus 1. So we have 3 terms instead of 2. Now, the rest of it is exactly the same. We're going to find a common denominator and work it out. Okay, so this right here is the challenge. Right there. Nothing else is new here. Okay. So let's try it. So we need a common denominator. So here a will have 2x minus 1, x minus 1. B will need just x minus 1. And c needs 2x minus 1 squared. So you multiply through all of that, and we know how to do this now. Here's all the steps. And then we'll consolidate all the like terms and set them equal to the left-hand side, which is x minus 2, which you'll see right here. Now, here, it can get a little messier solving for all 3 of these. Sometimes you just have to keep trying different possibilities. This can be a bit of a challenge, but ultimately what you're trying to do is solve one of these letters in terms of the others, or if you're really lucky, in terms of a constant. Like I would immediately go for this one because that is so easy to see. Whoops, what did I do? I got negative 2c, which means that can go into either of these two equations or both. Okay. And then I've got two equations in terms of just b and c. Let's see, is that what I did here? Yes, it sure is. Okay, good. And so, like I said, once that's done, I'm going to replace the a's in this equation and this equation with negative 2c. Oh, minus c minus b. All right, let's see. Just making sure. So if I want to, I can now solve for b directly. I'll add b to both sides. Just double checking. No, I knew something. No, I got it right. I'm looking at the wrong thing. This is at 6c plus b minus 4c equals 1, 2. I'll tell you what, let me do it. I'm writing it in a very clumsy way. Let me just continue with this one first. 2c plus b. There we go. All right, I think that's the way to go. B equals 1 minus 2c. So we have a is minus 2c. B is 1 minus 2c. So therefore, b equals 1 plus a. Well, and then we plug these in to the original equations. So two at a time. In other words, if you go back to the beginning, we had of the three equations, we had these three. So what we're going to do is take one of the equations that has a, b, and c and replace two of the three of them. So it looks like what I chose to do is, oh, it looks like I picked the last one. A minus b plus c equals negative 2. Combined with our knowledge that a is minus 2c and that b is 1 minus 2c. When we plug those in, we can prove now that c is negative 1. Once we have that, obviously these others are done too, because b is 1 minus 2c, 1 minus 2 times negative 1, or just 3. And of course, that implies that a equals negative 2 times negative 1, or just positive 2. That's really the worst part of all this, I think. So here's what we end up with. Now, we already shown that this is correct. And so now we'll replace A with 2, B will be replaced with 3, C with -1. Okay, so that comes up in the next slide. I plugged in all the constants. Now you can see that actually all three of these could, if you do it correctly, be solved for with U substitution. Okay, so let's see how that would work. All right, so here it is again. Now, what we're going to do is the first one will have U equals 2x minus 1, which means du is 2 dx. The second one will let U just be this part. So that we'll have du is dx. And then for the last one, this will be my U. All right, so then we can rewrite these. Now, by the way, the only one that's going to run into trouble is this one. We don't have a 2 here. We have a 3, but not a 2. So let's do a little trick here. We'll just rewrite it ever so slightly. I mean, it's still the same thing, but now you've got du in the numerator. Okay. The other two are fine the way they are. Okay. So that's what I've done in the next slide. I've changed this one only so that now suddenly we have du over u plus 3 halves du over u squared minus du over u. And also just a quick reminder, for this one. Yeah, just remember u squared in the denominator is u to the minus 2. Its integral is u to the minus 1 over 1, -1. So when we're done, we'll have log u in the first case. In the second case, it'll be 3 halves u to the minus 1 over minus 1, which you see here. And then in the third case, since it's just du over u, it'll be the log of u. And then we have plus c. And now we go back and we substitute in. For this first one, u was 2x minus 1. For the second one, same thing. And for this third one, u was x minus 1. All right, and so I make all the appropriate substitutions, and we're all set. After all the dust settles, this is it. And again, you're invited to double check it if you want, or you can ask Symbolab. Okay, now there's one more thing we need to look at. Another complication that can result from this technique. We may end up with something which is called an irreducible quadratic factor. Like, for example, imagine you have something like this. We discover that it has no real solutions. Like x squared minus 1 would be a perfect example of that. I'm sorry, x squared plus 1. Because what you actually got here is x squared is -1. Oh no. So we call that irreducible. And how did this happen, by the way? If you remember the quadratic formula, of course you do. Nobody ever forgets the quadratic formula. We use it to solve for there are always two solutions for a quadratic equation. And so we can factor it and set each factor equal to 0, or we can simply use our quadratic formula. I much prefer the quadratic formula, but here's the thing. If b squared minus 4ac is negative, then the solutions are imaginary. And that becomes irreducible. By the way, when do you have this? If you have a parabola that doesn't actually reach the horizontal axis, that means you have imaginary solutions. That's how you can tell, just by looking. All right, so what if that happens here? What do we do? Well, we have to adjust our technique, our partial fractions technique a little bit. Let's take a look at an example of this. And so we see right away we can factor. Oh, by the way, don't forget to check the degree of this numerator is 1. Remember, that never changes. We have to make sure the degree of the numerator is smaller, strictly smaller than the denominator before we proceed. Otherwise, we have to do division. So we don't have a problem with that here, but what we can do is rewrite this as 2x minus 3, x squared plus 1. You can see irreducible. Okay, what do we do? Well, another wrinkle we haven't seen before is this. Oh, how do you like that? Instead of a over x squared plus 1, we're going to have ax plus b. So whichever term contains is the irreducible one. In the numerator, you'll have ax plus b, and then the c will go with this term. Okay, see, again, this is something we haven't had to deal with before. Because before, we would have taken that quadratic expression, broken it up into factors, and then we would have had 3 terms. But now we can't do that. So this is how we work around that problem. But now the rest is exactly the same. I'm going to find common denominators, set the 2 numerators equal to each other. And so let me just show you quickly how that algebra goes. So here's the bottom line. And then you can see here that a plus c equals 0. B equals 2. And c is negative 3. And that implies that a equals 3. Okay, so we'll put that back into our original expression. This one right here, I mean. With a quick reminder that a is 3, b is 2, and c is negative 3. Okay, so this is what we have. Now, this is not going to be as straightforward maybe as it looks. We can't just do simple u substitution. The first expression, this one, needs a little work. This one is fine. We can use u substitution. So let's take a look at this one. 3x plus 2 or x squared plus 1. So we'll break it up into 2 pieces. Now, you're going to be surprised by this one. So, and then I broke it up again at 3x over x squared plus 1. And then here we have 2 times 1 over x squared plus 1. So now we're going to look at this term by itself, because it can be solved with u substitution. So that brings us here. And so what we're going to do is let u equal x squared plus 1. Du would therefore be 2x dx. We don't have that, but we can create it ourselves. And so this brings us to 3 halves du over u. And that just brings us back to 3 halves log u, or 3 halves x squared plus 1. Okay. So this term, I'll just make a note of it here. We just proved equals 3 halves ln x squared plus 1. Now this one, tricky. Guess what? If you go to your book and look at that chart, which I will find right now for you, of integrals, just integrals. Here's an interesting looking one. The integral of du over a squared plus u squared equals 1 over a arctangent u over a. So we have an x. Now, here's what we're going to do. Think of this as a squared and u squared. So if a equals 1 and u equals x, then this integral on the top here is 1 over 1 arctan u over 1, or very simply arctan u. And since u in this case is x squared plus 1, sorry, u is x. That means we just have this. The 2 is coming from here, by the way. It's simply the arctangent of x squared plus 1. So let's go back here. So this integral, remember way back, this problem has 2 integrals we had to solve. So let me just gather up all the information that we have so far. We just got through showing this equals three halves plus 2 arctan x. And then this one is very simply 3 ln x. Oh my God. Oh, sorry, I just realized this is x squared plus 1. Okay. Yeah, I copied it incorrectly. It's arctan x squared plus 1. Okay. So at long last, that's the answer. Wow. All right. So anyway, so we're actually done now with our discussion about integration. And so what's coming next, we're going to jump ahead to 5 in the book. Let me go back to the table of contents. So we're going to go to directly to 5 and 6, sequences in series and power series. Okay. That means we'll be covering everything we need to know for Calc 2. Some of these topics, I mean, the book has a lot more topics, which, like, for example, intro to differential equations, you can read up on that if you want. If you're a math major, you'll almost certainly end up taking a course in differential equations anyway. So it's kind of an interesting area, but it's very specialized. So we'll save that. You can save that for your actual differential equations class. In the meantime, we'll continue on with sequences in series, followed by power series. And then you'll be fully prepared for Calc 3 if you choose to take it. So anyway, so next time what I would like to do is maybe run through a few practice problems with this partial integration stuff, partial fraction, I mean, and then we'll dive into chapter 5. Okay, so I'll see you then.